Two bars are resting on a horizontal surface. They're connected by a light spring. Let's draw the picture. That's the horizontal surface. We have these two bars. So you can take them as blocks. Now they're connected by a light spring. So by light, they mean it is massless. The spring constant is not given, but we can take it as K. Okay, so the masses of the blocks are M1 and M2. The coefficient of friction between the bars and the horizontal surface is same, and then it is given as mu. We're asked to apply, we're asked to find the constant force that you must apply horizontally to the bar of mass M1 so that we are able to just move the other block. So the other block should just shift, okay, should just dislodge from its position. So we need to find the force value. So this is the minimum force required to move the other block. Okay, so here if we look at the free body diagram of the bar with mass m2, we will get an idea about what force is required to move it. What minimum force is actually required to move it. So the gravitational force m2g acts in the downward direction, and the normal force acts in the upward direction. Okay. The maximum possible friction that the surface applies on this part is mu times the maximum possible friction is mu times norm. Okay, so if I look at this friction force, we can say it is mu times m2g. So the spring is trying to pull this bar, let's say with some force kx. Now this force should be equal to this mu m2g in order to move this. So kx must be slightly greater, but in this case we'll just take it as equal to mu m2g. So if I have to move the block on the left, the extension that I need in the spring is mu m2g by k. Okay. Now if you look at the force applied, okay, so if you look at the force applied to the other block, let's look at what is happening with the other block. Okay, obviously this block must move, otherwise we will not get the extension, required extension. So this is obviously moving. Okay, and the spring is going to pull with a force. Okay, but this force is a variable force. It is going to change as the block goes away to the right. Okay, so this depends on the amount of extension, and because the block is moving, the surface will apply maximum possible friction force. Okay, so this is F max. Now here the earth is applying a gravitational force of m1g, and the normal force in the upward direction is equal to m1g. So the maximum possible friction force is mu times normal, which is mu times m1g. Okay. Because we are asked to calculate the minimum force required, the work done by the force should also be minimum. Okay, we are just trying to get this extension required, which is mu m2 by g, which is good enough to move the bar with mass m2. Okay, so by the time we achieve that extension, the m1 should not have any speed. Okay, so it should really come to rest. Okay, so here, if I apply work energy theorem by taking the bar with mass m1 as a system, we can get that minimum extension rate. Okay, so net work done is equal to change in kinetic energy. So now there are three forces which are trying to do work on the bar of mass m1. Okay, so the applied force F would do a work of F into displacement x. The spring force is in the opposite direction. So for an extension x, the work done by the spring force is minus half ax square. And the friction force is mu m1g. And for a displacement of x, the work done is negative here minus mu m1g x. So in order to get the minimum force, we're actually allowing that force to do minimum work. So that means we want the block to come to rest. Okay. So this is zero. The change in kinetic energy is zero. It is starting from rest and then it ends at rest. Okay. So here the force required is mu m1g plus ax by 2. Now, if we look at the value of kx from the discussion related to the free body diagram of the other block, that is mu m2g. So if I substitute here, we'll get mu m1g plus mu m2g by 2. So the minimum force required to move the other block is mu g multiplied by m1 plus m2 by 2.